Okay, so this is an inequality induction. So prove true for n equals 1, because I want it for positive n. So it's 2 times 1 factorial is greater than or equal to 2 to the 1 times 1 factorial squared. So that means 2 factorial is greater or equal to 2. So 2 is greater or equal to 2, which is true. Because 2 is equal to 2. Okay, let's assume true for n equals k. Okay, so we're going to assume that 2k to the factorial is greater than or equal to 2k times k factorial squared. Okay, and then we are going to prove true for n equals k plus 1. So it's nice to know what you are proving. So required to prove. So what we want to prove is this 2k plus 1 factorial greater or equal to 2 to the k plus 1, k plus 1 factorial squared. Okay, so this is what we're trying to prove, but we're going to use this one to actually prove it. So underneath this one, put A and C, because that's A is greater than C. And what we have to do is create a term in the middle, which is B. And in order to create the term in the middle, we use this here. We use our assumption when n equals k. So if you were continuing on with this proof, so go proof. So if you just go taking when n equals k, so you take 2k factorial is greater or equal to 2k, k factorial times k factorial, because that's what k factorial squared means. You do it twice. Now, if you take this and you want to try and get this one here, now a is 2k plus 2 when you expand the bracket. So we've got 2k factorial. So if we want to make a 2k plus 2, let's just understand what 2k plus 2 means. That's 2k plus 2, 2k plus 1, because you're just going down by 1, 2k, so 2k factorial. So that means it's exactly the same, except it's got this extra part here. So what we then do is we get that and we times both sides by 2k plus 2, 2k plus 1, 2k plus 2, 2k plus 1. Because you can see that's what's missing, these two here, on that there. Now, once I multiply by that, what will actually happen is, on this side here, the 2k plus 2, 2k plus 1, 2k plus 4, plus 2k factorial is the same as 2 factorial is greater or equal to 2k, k factorial squared times 2k plus 2, 2k plus 1. Okay, so now I need to do, so this is like your A and this is your B. So this is like when the same as when n equals k plus 1, that's what's written there. And what we want to do is, we know that it is bigger than B because this is the assumption, and the assumption was true. So if I do the same thing to both sides, it will still be bigger than B because you're multiplying a positive integer on each side. What we would like to do is we want to prove that this part here, which is B, we want to prove that's greater than or equal to C, which is 2k plus 1, k plus 1 factorial squared. Because basically, if B is bigger than C, and we know that A is bigger than B, then A will be bigger than B and C, and therefore A will be bigger than C. So therefore that one would be bigger than that one, is actually what we require. Now, I'll just rub this out just so I can create a little bit more room. So now we're going to be required to prove that 2 to the k, k factorial squared, 2k plus 2, 2k plus 1, so that should be, we want to prove that that's bigger than 2k plus 1, k plus 1 factorial squared. Okay, so when you go to cancel here, you got the 2k and you got the 2k plus 1. The 2k plus 1 is bigger. So 2k plus 1 minus the k will just give you 2 to the 1. So when you cancel that, you're going to get 2 to the power of 1. If you look at this part here, you've got k plus 1 factorial squared. So that is equal to k plus 1 times k factorial. So that means that when you cancel this one with this one, what will be left there will be k plus 1, because that's the extra term on the k plus 1, k factorial. But we need to square it, because we need to do it twice. It's like having k plus 1 factorial, k plus 1 factorial on this side, and on this side you have k factorial, because you're squaring it. So this is k plus 1 times k factorial, and this is k plus 1 times k factorial. So when you go to cancel here, you can see the k factorial from both sides will cancel out, and you're left with k plus 1 squared. Okay, so in my cancelling now, I have this left. So I have the 2k plus 2, 2k plus 1, greater than or equal to 2, and then I have k plus 1, k plus 1. Now, if you look at this and you just factorise out the 2 out of this one, then you end up with 2, k plus 1 is greater than or equal to 2, k plus 1, k plus 1. So that means the 2's on both sides will cancel, the k plus 1 will cancel, and you're just simply left with 2k plus 1 is greater than or equal to k plus 1. Remember, this statement is true because this was all derived on the original statement when n equals k, and I've just multiplied both sides by the extra part, 2k plus 2, 2k plus 1. That's what's in yellow up there. Now, when you're simplifying this, if you bring it to the one side, you have 2k plus 1 minus k minus 1. Is that greater than or equal to 0? 2k minus k is just k, and then minus 1 plus 1 is 0. So you just end up with k is greater than or equal to 0, which is true. So therefore, if true, and then if n equals k, then true for n equals k plus 1. But it is actually true for n equals 1, so therefore true for n equals 1 plus 1, which is 2, and so on for all integer values of n. Okay, or we could just say by the process, so you should put it therefore, by the process of mathematical induction, is true for all positive integer values of